Hey all, welcome back to my channel. So in today's session we are going to talk about Verilog tutorial. Like we are going to discuss about all the concepts in Verilog at one shot. Okay, so this will be helpful for those who are already aware of Verilog language, and if you want to have some deeper knowledge on all the concepts on Verilog, so please go through this video so that it will be helpful for you in order to have a reference for all the concepts in Verilog, right? And if you want a detailed explanation about all the concepts that I am mentioning today, I'll be linking that particular playlist in the description box. You can go there, check it out, where I have uploaded all the videos separately along with examples in that video. So you can go there and check it out, right? So today we are going to talk about Verilog HDL. So before going into like what are HDLs and what is Verilog HDL, just first let us start with VLSI design flow. Like how the design is flowing, like before creating the chip, what are the steps that are been undergone before creating a chip, right? The first thing is specification. So you already know what is specification. Specifications are nothing but requirements. Okay, when you are designing a circuit or when you are designing certain chip, okay, that particular thing should have some requirements. Like if you are designing something, okay, it will be having requirements like the power it is going to take, or the inputs that it is going to take, and what is the need that we are creating the chip. Okay, so all these requirements will be coming under the specifications. So we can call that all the requirements that are needed to design a chip, they will be named as a specification. Okay, so based on these specifications, the RTL design engineer, what he will do, he will be writing a code, RTL design code. Okay, so after RTL design engineer writes this RTL design code from the specifications that is given by some consumer or someone. Okay, so this RTL design code is simulated, and after simulation it will be going into the verification stage. So in verification, what is happening here is, if you are designing certain circuit, like for example let us consider if you are designing an adder. Okay, so this verification engineer, what he will do, he will be giving the stimulus is nothing but a group of data. Like for example, he will be giving the inputs like 2 and 2 to your RTL code, and there the logic has to be take this 2 and 2, and it will be taking undergoing that logic, and then it will be coming out like the output should be 4. Okay, if you are giving 2 and 2 and it is giving 4, then it is fine. In the same way, what will the verification engineer will do? In this way, he will be sending some group of data, not only one input, like all the possible inputs. Okay, so for all these possible inputs, your particular design should give the expected outputs. If your particular design is not giving that particular expected outputs, then the verification engineer will detect the bug in it, and again it will be sent to the RTL designer. Then again RTL designer will be modifying that particular bugs, and again undergoing simulation, and then again verification. So this process will be continuing until your particular RTL design code is bug free. Okay, then after verification it will be going to the physical design and then coming to the manufacturing, packaging and testing process. Okay, so this is the design flow. Like when you are designing something in VLSI, this is the particular steps that you are undergoing, right? So based on this specific, like based on these steps, again the VLSI is categorized into two parts, like front end VLSI and back end VLSI. So basically if you see here, RTL design, simulation, verification, so all this will be a coding part. Like you will be writing the code and you will be verifying it, and again it will be modifying when there are any bugs. So everything is done in a coding way, so that is why it is categorized into front end. So in front end, you will be dealing everything regarding designing and testing part, like coding part. Okay, for this coding, you need to know the languages called HDLs. Okay, for backend, it is for development and fabrication, like for fabricating the chip and for manufacturing, and everything will be taking under this backend process. Okay, so this is about front end and back end. And if you are a front end engineer, you can expect your opportunities in this particular fields. And if you are a back end engineer, you can expect the opportunities in these particular domains. Even though you're front end or back end engineer, VLSI industry in India, like a semiconductor industry, is having a rapid growth in India. So if you're some undergraduate or if you're studying an engineering or a fresher, okay, and if you're interested in VLSI, you can choose either front end or back end based on your interest. Like if you are interested in coding, you can choose the front end or back end, but in front end you can have more opportunities compared to that of back end. Okay, and also the pay is little more in front end compared to that of back end, right? So this is about the front end and back end. Now in front end, what are we going to learn? Like in front end, as I told you, everything is related to coding. So for coding, we need to learn a language. So what are those called? They are called HDLs, Hardware Description Languages. Okay. So in order to survive in the front end, you need to know certain languages like Verilog HDL, System Verilog, and UVM methodology. Okay. So you need to be familiar with these two languages. Not only you should be familiar, but you should know in and out about these two languages like Verilog HDL and System Verilog. And then you should also be familiar with universal verification methodology, right? So this is about the previous, like before going into HTLs, what is actually happening in this VLS industry. This is introduction for this, right? And now coming to HDL. So if you are a front end engineer and if you are interested in design and verification domain, then you should learn Verilog HDL, System Verilog, and Universal Verification Methodology. So this Verilog and System Verilog are called HDLs. HDL is nothing but Hardware Description Language. So what does this mean? So hardware description language is a programming language which will describe the structure, behavior of the circuit. Okay, so simply putting in simple words, HDL is nothing but text format of the design that you are designing physically. Okay, for example, if you are designing an adder, okay, before designing it physically, you will be writing it in a text format, in the coded format, which is by using the HDL. Okay, simply. Okay, that is the simple meaning, like what is HDL. Okay, but even though in the previous I have told you that this is a programming language, yes, HDL is a programming language, but not a software programming language. Why? Because if we go into software programming language, any language will be used in order to create a software. But in this hardware description language, we are actually describing something. That is why that is called as HDL. What are we describing? We are describing the behavior of the circuit. Okay, so based on the behavior of the circuit, based on how we are describing, in that way only the physical circuit is being created by the PD, like backend department, right? So this is about HDLs. So it is having so many advantages, like HDLs are having so many advantages like reusability, flexibility, lower costs, and also for better simulation. Like basically, by using HDLs, the simulation is much more improved. Why? Because we can easily find the bugs, and then the bugs can be modified by the design engineers before they can actually go into the physical formation. Like before fabricating the physical chip, they can be easily modified by using this HDLs. Okay, and also you are having many reusability and flexibility purposes. Okay, now coming to Verilog HDL. So what is Verilog HDL? So actually this HDL is again, when we see in the real-time industries, most frequently two types of HDLs are used. One is Verilog HDL and then VHDL. But mostly almost 70 to 80% industries will be opting this Verilog HDL. So why? What is the reason behind opting the Verilog HDL rather than VHDL? Why is it? Because Verilog is very easy to learn and it is easy to understand, and also the syntaxes are familiar with many other languages like C, C++. Okay, the syntaxes that you are using in Verilog are very similar to C language, and even though you don't know C also, you can easily understand it. Also it is a case sensitive language, right? So basically most of them opt for Verilog HDL rather than VHDL. So in this video we are going to talk everything about Verilog HDL. So as I already told you, Verilog is very easy to learn and it is similar to C language, right? And in Verilog, when you are writing a code, you can opt for 4 different abstraction levels. Okay, that means you can have 4 different coding styles while you are writing a code. Like you can have behavioral coding style, data flow coding style, gate level coding style, or switch level coding style. Right? When you are writing a program, you can write in any of these 4 abstraction levels. Right? So this is about Verilog HDL. So now we are going into the language. Like what does this actual Verilog HDL consists of? So as you already know that Verilog HDL is a programming language, right? So any program is built with some syntaxes and some um, properties, is it or not? So basically in Verilog, when you are building a code, okay, everything you will be built within the module. So we can call these modules as basic building blocks. Why? Because whatever code you are writing within the Verilog, you will be writing within this module and end module. Like if you see here, within the module and end module, you will be writing the implementation is nothing but the entire code will come under this particular thing. So it is module describes boundaries, like within the boundaries you will be writing and module followed by module name along with ports list. Okay, so this is how you will be writing your code, like module and module name followed by ports list, right? So within the implementation you can write any, like you can use behavioral modeling as we discussed before, or we can have data flow modeling or switch level modeling, anything you can implement, right? So let me show you a small example here, right? Within the module and end module, for example, if you are writing a full adder code, okay, module, any name, this can be of any individual name. Here I am just mentioning it as full adder else. So within this, okay, within the parenthesis itself, I am mentioning the ports like ABC, and like if you see here for full adder, you will be having 3 inputs and 2 outputs, sum and carry. Is it or not? So the 3 inputs and 2 outputs are also mentioned within the module and end module, and this is the logic which is implementation and end module, right? So in this way, any code you are going to write, you will be writing within the module and end module. Now coming to the important topic, which is module instantiation. So what is this module instantiation? So put it in simple words to make you understand simply, it is just like a copy. Okay, if you see the word, if you see the dictionary word for instances, what is the meaning of instances? Instances means copies. So what are the copies? Copy is nothing but, here for example, okay, let me explain it with an example so that it will be easily understood for you. For example, I am writing a half adder code here. If you see, this is my half adder code. Okay, and this is my half adder. Now, I want to write a full adder code. Okay, but for this, what I am doing, I want to design a full adder by using 2 half adders. So, if you don't use any instantiation here, what you will do actually, you will be writing codes for 2 half adders separately, and then you will be creating one module for this, again one module for this, again for these two, again you will be adding this particular carry adder or get, and again for this you will be adding the sum and cout. So in this way you need to write everything. Like if you are going to write, for example, if you see the code here, it is consists of some 10 to 15 lines of code for half adder. Now if you are writing the full adder by using the same 2 half adders, you need some 30 to 40 lines of code in order to write. Is it or not? So while simulating your code, what happens, the lengthier your code is, the simulation, the more simulation time it takes. So that is why, in order to reduce the time, memory and everything, so what have we done here is, in Verilog you are having a concept called instantiation. This is the reusability that is we are talking about in the before topics, like advantages. In case of advantages of HDL, the first thing we have discussed about is reusability. So what does the reusability mean? Based on these concepts, okay, not only instantiation, we are having various other topics which will help in reusability purposes. So here what actually we are doing, we will be writing a half adder code here. Okay, one time we will be writing the half adder code. Okay, if you see here, this is my half adder code with the name half adder. Okay, so now by taking that half adder name, you are creating two instances. So this is my half adder. Okay, and now I am creating two instances for this, like HA0, HA1. So by creating two instances, nothing but two instantiations you are creating, two copies you are creating, and you are taking again the individual ports. Like if you see here, it is having A, B, S, C as ports. Like here, C in and S sum and C1 are its individual. So if you see here, when you are creating instantiations, every instance will be having its individual port connections. Clear? So this is how the instantiation helps in reusability purposes. Like you are creating a copy for the actual parent module. Yeah, what is the instantiation means? You are creating a copy for the parent module, and by taking that copy, you will be connecting the ports individually, right? So this is about the module instantiation. Hope it is clear for you. If you see here, these are the instantiations, module instantiations. Okay, so module instantiation is very important. Why is because as I told you in verification, in the starting, like in the design flow, VLSI design flow, we have discussed that in verification the verification engineer will be sending some stimulus to the RTL. So how you will be sending the stimulus from test bench to RTL? You need a connection. So how you will be connecting? By instantiating that design to the test bench, you will be connecting this ports and that ports. Okay, you will be discussing it in this video itself. I'm just giving you some hint, like what is the instantiation and where is it actually used, right? So this is about module instantiation. So before going into, like, every language will consist of some tokens, lexical tokens, like basically some syntaxes we need to know before writing a code. So these are some of the syntaxes that you should know before going into the Verilog HDL, in order to avoid any semantic errors. Because during simulation, because every code is built with some syntaxes, you should know that syntaxes in order to write your code correctly and in order to simulate it perfectly. So that is why, in order to avoid any syntax or semantic errors, you should know about these particular topics. So I don't explain in brief about all these things. Okay, I'll just give you small explanations on these things. Like white space, if you see, you should know at which point of time you should give the space and which point of time you shouldn't give the space. Okay, so that is important. Like if you see here, end module, if you see this is the keyword. Okay, between the end and module you shouldn't give white space. So that is the syntax. You should know where to give and where not to give, right? So this is about white space. And then coming to comments. Okay, comments are actually, if you don't want any particular logic to be activated at that particular point of time, you can just keep it in comments. So basically, this is not the only purpose for comments. Basically, if you see the codes, whenever you want to explain your logic to someone, as soon as they see the particular code, if you want them to understand your code, mostly everyone prefer writing the logic, like why they have written this particular logic, in the comments. Okay, so comments are useful for that also. Basically, in Verilog, just like in C language only, here Verilog syntax is also same for comments, right? And then coming to operators. Operators are very important. Like based on all these operators only, you will be writing your logic. Okay, so without these operators, you can't write the logic in the data flow modeling, right? That is why, so operators are very important. And in Verilog, you are having various categories in operators. Like, see, if you see arithmetic, relational, equality, logical, bitwise, reduction, shift, conditional, concatenation. So based on using all these operators only, you will be writing the codes. So these are the symbols for operators. You can just pause it and just check out these operators. Okay, if you are confused about the operators, you can just pause this video and check this particular video. And if you want the clear explanation of this, as I already told you, I link that playlist of Verilog HDL tutorial in the description box. You can go there and check every video you want, right? So now coming to some lexical tokens. One of the lexical tokens is constants. So constants is nothing but when you are assigning some value to a variable. For example, a equal to 5. Okay, 5 is assigned to some variable a. So in Verilog you can't just assign it simply a equal to 5. Why? Because it needs some syntax. So what is the syntax? In order to assign some constant to a variable, you should follow this syntax. Like first you should give the size. Okay, so what is the size of the bit? Like if you see here, this is the 4-bit size, tick. And next is radix. Radix means whether it is of binary or decimal or octal or hexadecimal. That is the radix, which format. And then the value. Value is nothing but which value you want to assign. So in this way, you will be assigning the values. You needn't just give it like this. Even though if you are giving it like this, you will be having some things. If you see here, if you are giving it just like 14, now what is it? This is the unsized decimal. So what happens if you are just giving it, even though you are creating it as a 14 but extended to 32 bits, but even though you are not mentioned, since you didn't mention any size, so the automatic 32 memory locations are created. Okay, so because by default the unsized decimal's default value is 32 bits, so if you're not mentioning any size, it will be taking a 32-bit memory locations. Because of this, there will be wastage of memory. Okay, so that is why if you are a beginner and if you are writing a code, okay, it is advisable to write anything by mentioning the size and radix also. Okay, so this is the sized constants. If you see here, these three are sized constants. This is unsized constant. So unsized constant is obviously 32-bit by default. Okay, and if you want to assign any x and z values like unknown values, high impedance values, because these are for x and z values, you will be mentioning it like this. Okay, for real numbers, and this is for negative numbers. Like so, these are some basic constants that you will be seeing in the Verilog language. Then coming to identifiers. So identifiers are nothing but they are just the names. Okay, for example, in the previous example we have seen that module we have given half adder. So that half adder is a name. You can give any name you want. Okay, identifier is nothing but just a name, and you can give any name, but you should follow certain rules while you are giving the identifiers. So why are these identifiers needed? Like for example, if you are writing some function and if you don't name it, how can you call it at some point of your program? Similarly, you are creating an instantiation, module instantiation, without naming your module. How can you instantiate it? Is it or not? So that is why identifiers are important. And also it has certain rules, like you can use any of these alphabets from uppercase A to Z, smaller case A to Z, and 0 to 9. And for special characters, only these two are allowed, like underscore and dollar. The remaining all are not allowed. And also the identifier should not start with these two things. Okay, and it should not contain only numbers, but it should not contain any white spaces, that means any gaps in between the names. Okay, keywords cannot be used as identifiers. You can use any underscores. Okay, like if you see here, these are some examples. Why are these four invalid identifiers? If you see, because it shouldn't start with number. It can contain numbers, but it shouldn't start with number. It shouldn't contain only numbers. It shouldn't contain the special character, and then here it is space. Okay, so this is how, if you want to give a name, you should give it based on all these rules and regulations. And if you don't want to follow all these rules and regulations, there is a way, which is an escaped identifier. So escaped identifier means if you don't want to follow any of these rules but you want to make this as a valid identifier, you should just give a backslash before. When you are mentioning a backslash before any identifier, then that is considered as escaped identifier, and because of this the simulator doesn't throw you any error. Clear? So that is about identifiers. Now coming to Verilog keywords. So just like in other languages also, in Verilog also you are having some inbuilt keywords within this particular language. Okay, so these are some of the Verilog keywords, not all the Verilog keywords, but in the Verilog these are some of the keywords that you will most frequently use. Okay, so if you see, all the keywords are in lower sensitive, they are case sensitive and they are of lower case. Okay, so these are already inbuilt in the Verilog. You can just use them wherever you want, right? So this is about the lexical tokens that we are discussing about. And now coming to the next important topic, which is data types in Verilog. right? In data types in Verilog is very important, and among the data types the most frequently used are nets and registers. So again, registers are subcategorized into two types, like various types like reg, integers, real time. Similarly, nets are also subcategorized. Now let us see what are these data types. Okay, so first coming to net. Net data type is nothing but, for example, as I already told you, when you are designing a circuit or when you are designing something, and when you want to connect one component to another component physically, what you will do, you will be connecting it with the help of wire. Is it or not? Similarly, when you want to connect one element to other element, or one module to other module, okay, in particular code, what you will be using, you will also be using wire. Okay, but that wire is by using a wire keyword instead of physically creating a wire. So what does this wire do? It will send the data from one component to other component. So simply, just like a physical wire, what it does, it will be sending the information from one point to another, not information or anything, it will just sending anything from one point to another. Similarly, in code also, in Verilog language also, wire keyword, what it will be doing, it will be sending the data from one component to other component. So simply we can take that wire is the something, is the data type which is used to drive the value. So the work of the wire in Verilog is to drive the values, that's it. Okay, so by default the value of wire is z. Okay, if you don't mention, like if you don't give any value to this particular wire, it is z. Actually, nets are declared with keyword wire. Okay, most in codes you will be using the keyword wire. Again, this wire is subcategorized into various types like w and w, or try and supply 0, supply 1. Okay, so this is about wire. Like net data type, in net data type it is mostly we'll be using a keyword called wire is used to drive the values. It is just used to drive the values. Like if you see this particular code, okay, here a b c are inputs, y is output. So all the input and output ports are declared within the particular module. But if you see here the intermediate connections, if you see here, you don't need to mention this intermediate connections within the ports list. Okay, you can just use wire or rich data type in order to give all these intermediate connections a declaration. So if you see here, mostly all the intermediate connections will be given as wire. Okay, so wire T1. Clear? So if you see here, if you see this particular full adder circuits, here A, B, C in are inputs and sum and C out are outputs. So input and outputs are declared within the module. Now if you see here, you are having some intermediate connections here. So all these intermediate connections are given for wire. Right? Got it? So this is about wire. So just if you see here, what is this doing? C is just used to drive the value from this gate to this gate. Okay, so that is what it is doing. Similarly, C1 is used in order to drive the value from this point to this point. Okay, so you can just remember it like that. Wire is just used to drive the values. Okay, now coming to register data type. So it is entire opposite to wire. Like what is wire doing? It is driving the value, that it is sending the value. So okay, for sending the value we are having a component. Then for storing something you need to have another data type, right? That is register data type. Okay, so reg will be holding the value instead of driving the value. It will be holding the value, like it will be holding until it is replaced by other value. Clear? So this is about register data type, and by default it is of value x. Okay, and it is declared by the keyword reg. Okay, right? For net you will be using the wire keyword, and for register data type you will be using the reg keyword. Okay, clear? So in order to store the value you will be using this register data type. It will be retaining the value until another value is placed onto them, right? So this is about register data. Again, register data type is again categorized into reg, integer, real time, etc. Okay, Now if you see here, the same program, but here in the previous I want it to drive the value, but now here I want t1 to be used as storage value, that I want t1 to store some values, hold the values. That is why I'm mentioning it as rich. So if you are using it as t1 as rich, then the t1 will be holding the value. If you are using it as wire, then it will be driving the value. Clear? Yes. Now coming to integer data type, like integer, just like reg and net data types. Okay, integer is also a data type which is used in order to declare some numbers. Okay, when you want to declare it in a number format, then you will be using the integer data type, and by default it is of 32-bit register. Okay, so this is declared by keyword integer. Similarly, real also, for storing the real values, like floating values. In order to assign floating values, you will be using the real data type. Now coming to time. So what is this time? Basically, when you are simulating some code, or when you are doing some code, okay, you need to know at some particular point of time if you want to know the simulation time. So what is the simulation time? It is nothing but an amount of time which is spent on simulating the module. Okay, like how much time it is, your particular, if you are having some 10 lines of code, okay, at fifth line of your code, how much is, what is the simulation time, like at what point of time this fifth line of code is being executed, being simulated, sorry. So all this, in order to know, you will be using this time data type. Okay, by using the $time keyword system function, okay, you will be in getting the value of the simulation time. You will be knowing the current simulation time by using the $time system function. Clear? So this is about Verilog data types. Now, if you see here in the previous, we have talked about, while we are talking about region net, okay, all the region net data types are scalar data types. That means they are single bit data types. Now, if you see here for integer, it is a 32-bit by default, but for region wire, by default they are of single bits. Okay, so single bit is nothing but scalar bit. Now if you want to increase the width of the bits, okay, how can you do? By using the vector representation. Okay, so scalar means single bit, and if you want to increase the magnitude of, if you want to increase the width of that particular variable, then you can be using this vector representation. Okay, how are we going to represent vector? If you see here, wire x. Okay, so if you didn't mention any width before, so that is why it is a scalar. So by default it is scalar, right? So x, y, z all are scalar values. Now if you want to increase the width, how you will be doing? You will be mentioning the width, like 5 down to 0, so this is of 6 bit. Similarly 7 down to 0, 8 bit. 11 down to 0, which is 12 bit. So in this way, in order to increase the width of that particular data types, you will be using this particular scalar and vector representations. Right, now coming to Verilog arrays. So if you see, for example, like reg a, okay, this is my particular a. Now if I want to take, okay, some register data type, I want to take some 10 variables like a1, a2, a3, similarly up to a10. If I want to take 10 variables which are of same data type, is it possible? Yes, it is possible through Verilog arrays. So Verilog arrays means ordered list of variables. So ordered list of variables which are having the same data type. Okay, if you want some group of variables which should contain the same data type, and instead of mentioning every variable individually, you can just by use define it by using a Verilog arrays concept. So if you see here, this is how you will be representing your array, like register a 3 down to 0. That means here if you see, here a, it is similar to a1, a2, a3, a4. Instead of creating a1, a2, a3, a4 four elements individually, you have just taken one variable name which is a, and I am taking the width, I am increasing the width of this particular element. So what happens? This is called array representation. Now you may get the doubt, like if you see here in the before we have talked like this is the vector representation and this is the array representation. Now how will you differentiate between vector representation and array representation? So you can if you are confused about it, you can watch my full length video, but I don't want to skip it now. I will also explain it here, but not in a brief manner, just in simple words I will be explaining how to differentiate between array and vector representation. So basically if you see here, like what is the difference actually, like here a7 down to 0, this is the array representation. Why is it array representation? Because here if you see, okay, a7 down to 0, that means here from a1 to a7, here I am having 8 elements. Okay, that means 8 memory locations are created here. That is what happening here. If you see here, 8 memory locations are created here, and 8 memory locations can hold only single bit. Why? Because here I didn't give any width. Okay, for example, if for the same for the same example, if I have given it like that, 1 down to 0, a7 down to 0, now what happens? It is having 7 elements where each element can hold 2 bits. Like why? Because a is having the width of 2, so here every element can hold 2 bits, like 1 1 0 1 1 0 1 1. Okay, similarly if you are making it 2 down to 0, then every element can hold 3 bits. Clear? So this is how the actual representation, like why is it happening here like in this way, like this is array representation, and if you want to increase the width you should give it before. Okay, so simply we can say that if for array representation, okay, if you are representing array, then it should be after the value, after the particular variable. You can just remember it like that. Okay, it's just some kind of remembrance for you. Okay, how to differentiate between array representation and vector representation is, if the representation is given after, if the width is mentioned after the variable, then it is array. After array, you can just remember it like this. Okay, and the opposite of this, if the representation is before, then it is considered as vector representation. Okay, this is just a for remembrance. Okay, but you should also know the reason behind it before going into remembrance. Why? Because these are just tips in order to make you remember when you enter into some interviews or some written test. Okay, because of some tension and because of some other issues also, you may forget, even though the logic you know it, you may forget it. So in such, at such times you can remember by using these tips. But also, even though you remember the tip, you should also know the reason behind it. Like I have told you how, what is the like actually happening, what is the array representation and what is the vector representation, how to differentiate between these two. That is what here. See, a vector is single element that is having n bits. Like if you see here, this count is the single element, okay, which is having 4 bit wide. Now if you see here, count will be 1011, so this is my single element, okay, which is having a 4 bit wide. Now if you see here, for the same array, here this count is not a single element, but here this represents count 0, count 1, count 2, count 3. So 4 elements where each element can hold 1 bit. Okay, if you see here, if you see this example here, having 4 elements, what are those elements? Count 0, count 1, count 2, count 3. Okay, where each count can hold 8 bits, right, where each element can hold 8 bits. Clear? So this is what the differentiation between vector and array. So in Verilog arrays, you are having various kinds of arrays like one dimensional, two dimensional, three dimensional arrays. So this is how you will be representing the array after the variable name. Okay, and when you want to assign the particular value for that particular array, by using that memory location you will be assigning the values. Okay, so you can just pause this and see these particular examples, and if you are having any doubts you can ping me in the comment box. right? And now, so this is about the basics of like what are the things that we need to know before going to write a code in Verilog. So coming to the Verilog module, you already know about the module, right? So what does this module consist of? Like module name, we have already seen it. Ports list, okay. Declarations, like what are the declarations, like input and output ports. And then if it is behavioral modeling, you will be using the always statement. If it is a data flow modeling, you will be using the continue statement. If it is a gate level modeling, you'll be using the gate instantiations. Okay. And then direction is nothing but which direction it is, whether it is input or output, right? So now going into the second concept in the module, like if you see, you have seen module name and instantiation. Now coming to ports list. So what is the ports? You already know about the ports, like which port it is. Basically when you are designing anything, it will be having two ports mostly. Okay, in Verilog you are having three ports obviously. Mostly you will be using input output. Okay, you are also having another direction which is in out here. Okay. So, like how you will be declaring the ports. We have already seen this. If you want to declare the ports, you can do it either inside the module. Like you can declare the module only with the names of the ports, and you can declare the directions inside the module. Or you can directly declare within the parenthesis both the names as well as directions itself. Okay, but don't mix and match both things. That means don't declare within the parenthesis and also inside the module also don't declare it, because it will throw you error. We should use either this method or this method. Don't use the both the methods at a time, right? So this is how you will be declaring the port. Now coming to connections. Connections are really important for ports, because based on the connections only, based if you see like when you are connecting some one element to another element, so based on these connections only the data transfer takes place, is it or not? So in order to make your data to transfer correctly from one port to another port, your connections are very important. So you should know compulsorily about this port connections. And also in Verilog you have a chance, if you don't want to connect any port, like in physical format, like when you are physically designing a chip, and when you don't want to connect some port of you, or if you want to leave the port as unconnected, what you will do, you will just don't connect that port. Similarly in coding also, if you don't want to connect any port, or okay, if you want to leave the port as unconnected, you can do that by leaving a space between the ports. Like if you see here actually you should have cout. If you see this is the full adder logic. Okay, you should be having the port like cout here. But if you don't want to connect this cout to any other element, so what you are doing, you are just leaving the space here. Clear? You can do that. And now coming to the connections, you can connect it in two ways. Okay, port mapping or port connecting, any other, both are same. Like port mapping by order, by name. By order means, so based on the order, like if you see here, this is my RTL code. Okay, this is my TB code. If you see here, so I want to connect my RTL to TB. I want to connect my RTL ports to TB ports. Okay, so how am I going to do it? You can do it based on order. So if you are doing it by order, then what happens, how you are mentioning the ports in your RTL, in that way only you should connect the ports. Now what happens, since your port listing you are connecting it by order, so then what happens, sign A is connected to A, out is connected to B. Okay, now for example, if you are doing it in this way, now what happens, out is connected to A, that means here output is connected to input. Okay, input is connected to output. Okay, now what happens, everything will be mismatched, like every declaration and every assignment of data, everything will be mismatched. So that is why you, if you are listing it by order, then you should compulsorily know that how you are mentioning the inputs in order, in that order only you should be connecting the ports. Okay, if you are connecting it by name, you don't need to follow the order. Now if you see here by name, like I want to connect this to this, so I am just giving dot a sig of a, similarly dot b to out. So I'm just mentioning it by name. Since I'm mentioning it by name, I no need to mention any other things. Okay. Now coming to the second one, if you see here, I can do this. I can just, if you see here, this is the same order. If you see here, this is, but even though I don't follow the order, now if you see here, B is the second one, but I have kept it in the first place. Even though I have kept it in the first place, it doesn't give you any error or any error output. Why? Because since I am mentioning it by name, so automatically B is connected to out only, even though you are not following the order. Okay, hope it is clear for you. Now writing a test bench in Verilog. How are we going to write a test bench code in Verilog? Okay, so what is actually this test bench? So in the verification, in the starting when design VLSI design process, I have told you verification engineer will be sending the input to the DUT. Okay, so it will be done in the test bench. So test bench is nothing but it is a environment where the functional correctness of your design will be checked. Okay, how will you design, like how will you check this functional correctness? Actually what will happen here is, from your particular TB, okay, from your test bench. So this is my test bench environment. From my test bench environment, I'll be sending the stimulus. Stimulus is nothing but packets of data. Like if you 01011, so this is my packet of data. So I am sending this stimulus to this DUT. So what is this DUT? This DUT is nothing but the RTL code that I am writing. Okay, RTL design, nothing but RTL design. Okay, so I will send my stimulus to this DUT, and here the process will be coming, and then the output is sent to the monitor. Like monitor will be continuously monitoring the stimulus that I am sending and the output that is sending from the DUT. Okay, so in this way you will be sending the stimulus. Okay, so this is how you will be writing the code for, this is my test bench code. Okay, this is my RTL code. If you see here, now you have to remember one thing: whatever inputs that you are mentioning within your RTL code, those should be given as rich. Whatever outputs you are mentioning, those should be given as wire. So y input should be considered as rich, y output should be considered as wire. Okay, I have explained in detail about this in the full length video of how to write a test bench code. Okay, this is that is also there in this particular description box, Verilog HDL tutorial itself. You can check it out, and if you can if you are having any doubts, you can ask me in the comment box, right? Yes. So again, when you are writing a test bench code, okay, the test bench code will be different for combinational and sequential circuits. Why? Because basically for combinational circuits you don't need to generate the clock, but for sequential circuits you need to generate the clock. So that clock generation is also done in the test bench itself. Okay, that is why one block is added for clock generation here. Clear? So this is about the test bench code. Right, now coming to the levels of abstraction. So we are having 4 levels of abstraction in particular Verilog language. Like first, the lowest level of abstraction is switch level, but switch level is not considered in Verilog. Why? Because that is the lowest level where you will be using MOS, like PMOS and MOS circuits. But when you are entering into the real time field, we don't need to go to that low level of PMOS and NMOS in order to design a circuit, because you will be designing a complex circuits. Okay, when you are using a complex circuits, you don't go for this PMOS and NMOS things, right? So that is why the switch level is almost avoided in case of Verilog. Okay, in Verilog you will be starting with gate level, which is considered as lowest level for Verilog. Okay, so gate level is lowest level and behavioral level is the highest level. So in gate level, by using the gates, logic gates like AND gate, OR gate, NAND gate, so based on all these gates you will be writing the code. Okay, in case of data flow modeling, based on the flow of data, like based on how the data is flowing between your registers, and based on the operators, you will be writing your code in case of data flow modeling. And in case of behavioral modeling, based on the behavior of the circuit, like how your circuit is behaving for a set of inputs. So keeping that in mind, you will be writing the code for behavioral level modeling, right? So coming to gate level modeling, here if you see, as I already told you, that this is the lowest level of modeling. Okay, and here you will be using, in case of gate level modeling, you will be using gates in order to write your program. Okay, so based on the structure, that is why this is called as structural level also. So based on the structure, you will be writing the code. So these are the basic gates you will be using. So all these are called as gate primitives. Like these all gates are already inbuilt in the Verilog. Okay, what you need to do is you need to just call this gate and you need to write a program using this particular gate primitives. Okay, so these are the gates that are already inbuilt in the Verilog. Okay, and when you want to call this gate, you have to, as I already told you, since they are already inbuilt, so they will have certain syntax. So you need to follow that syntax in order to call your that particular gate into your code. Okay, so these are the syntaxes for, like, for any gate. First you should mention the output, then the inputs. Okay, that is the simple logic here, right? So these are certain gates. Okay, you already know about this. You can just pause the video and check out all the gates if you are interested in this. Okay, so I'll show you a small example here. Okay, here we are writing a program for gate level program. Okay, gate level code for half adder. So as I already told you, since you are writing it in a gate level modeling, the most important thing in case of gate level modeling is the structure. Okay, the structure of your circuit. So this is my structure. So based on this structure, I'll be writing my code. So if you see here, what does my structure consist of? One AND gate and one XOR gate, right? So based on this AND and XOR. Okay, so for everything you should be considering the output. So what is the output? First output is sum. A and B are inputs. So sum A comma B, and you will be mentioning with some individual names. So gate name and input and output ports. Gate name and input and output ports. Simple, just as simple as that. Okay, so between module and main module you will be creating a name and then input and output ports, and then you will be writing, calling the gates and writing the code. That's it. So if you see here, what is the most important thing in order to write your code? This is not the logic that is important, but the gate structure that is important. Clear? So this is for mux. Okay, you can just pause this video and check the logic for this also. This is for full adder. Okay, here I am using instantiation topic. Okay, you can just pause this and check out, and if you want an explanation of this particular thing, you can go into my full length video where I have explained clearly about how this instantiation is taking place and how the port connection is being done, right? And this is how you will be giving the stimulus. Okay, these are delays. So this is how you will be giving the stimulus through your test bench. Clear? Yes. Now coming to data flow modeling. So in the gate level modeling, you will be writing the code based on the gates, based on the structure. But in case of data flow modeling, what you will be doing, you will be writing the code based on how the data is flowing. That is why this is called as data flow modeling. Like how the data is flowing between your particular registers. Based on that, you will be creating this data flow modeling. Okay, so in this data flow modeling, the most important thing is you will be using the assign keyword in order to write a logic. Okay, so in order to use this assign keyword, you have to follow certain rules and characteristics. So what is that? Here if you see here, assign LHS is equal to RHS. LHS equal to RHS means, for example, if you are writing for AND gate. Okay, so what is this is my AND gate. Okay, A and B are input, C is output. So what happens? Assign C equal to A and B. By using the operator symbols, you will be writing the code. Okay, assign C equal to A and B. Now this C is my LHS and this A and B is my RHS. Okay, so this LHS and RHS, while you are mentioning the LHS and RHS, you need to remember some important concepts. What is this? The LHS of an assignment must always be vector or scalar. It cannot be vector or scalar register. It should be only net. Okay, that means this C should always be wire data type, but not rich data type. You should remember that thing. Okay, the RHS can be of any data type, but the LHS should only be wire data type but not rich data type. So why is that also I have explained clearly while I explaining the data flow modeling. You can go there and check it out, right? So that is one condition. RHS can be of any registers, like it can be of net or any data type, but LHS should always be wire. Okay, so here what happens when you are using the assign keyword, as soon as the logic like A and B operation is done, then the output is immediately assigned to C. Okay, if you are having any delays, you can also use the delays in case of data flow modeling, right? So you'll be, if you see here, this is my logic. I have told you that I have using the operator. So in this way you can use all these operators in order to build your logic in case of continuous assignment, which is the data flow modeling. So this data flow modeling is called, in this the continuous assignment is being done. That means the assignment is done continuously to this particular LHS and RHS values. Clear? So these are the operators that you will be using, like arithmetic. So you already know about, in order to perform arithmetic operations you will be using the arithmetic operators, and in order to perform logical operations you will be using logical. So this is logical negation, logical and logical or. And in order to perform bitwise operations you will be using the bitwise operator, where these are the notations for bitwise operations. Okay, like and or. Okay, you should know, you should also consider the difference between logical and bitwise and. You should remember these particular operations. That is why I have created a separate slide for this, or else I would have just explained it by taking everything in within a single flow. But in order to make you also know about these operations, because when you are writing a logic in case of data flow modeling by using operators, the most important thing you should consider is the operator symbol. Operator symbol is very important, even though it seems to be very easy, but it is also a very confusing concept. So that is why, so if you are interested, you can just write a notes by take a snap of this particular operator symbols. Okay, and then coming to equality, again in equality you are having two types of equality. One is equality and the second is case equality. Okay, so the difference between the equality and case equality is, equality will be having four outputs, like the output can be either 0, 1, x or z in case of equality operators, but whereas in case equality operators the output can be only 0 or 1. You don't have x or z outputs in case of case equality. Like why? Because even though there are x and z values in, when you are using the case equality operator, then it will be comparing the x and z values also, so that you will be having only 1 and 0 as outputs. Okay, in order for detailed explanation, I have explained in detail about all these operators in my video. You can go check out there, right? Next is relational. In order to know whether a particular two inputs are greater than or less, in order to have a relational operators, you will be using a operation, perform relational operation, you will be using this relational operators. And for left shift and right shifts you will be using, so this is the operators for. Again here for left shift and right shift also, this is logical left shift, logical right shift. Okay, and this is arithmetic left shift and arithmetical right shift. You should consider that. Okay, you should also remember, like 2 means it is logical shift and 3 means that is arithmetic shift. Okay, now coming to reduction operators. Okay, so if you see here, these are similar to that of bitwise operators. So how will you differentiate between the bitwise operator and reduction operator? Okay, so basically in case of reduction operator there will be only one output, like only in single bit, either 1 or 0 only one output will be. But in case of bitwise operator, okay, that won't be the case. Like if, for example, if you are compare, like if you are ending these two cases, okay, in case of what is, in case of bitwise operator you will be having the output in a 4 bits, but in case of this particular reduction operator you will be having only 1 or 0 as output, only single bit, not multiple bits. Okay, why is that? Like how the reduction will be taking place in this reduction operator, you can go and check that in the full length video, right? Now coming to conditional operators. Okay, for conditional operators, if you see here, you will be using the logic. This is the main logic here. Okay, so the result equal to conditional expression. For example, Here I am writing A and B question mark 1 semicolon 0. Now what happens if A and B is true? Okay, like for example A greater than B. Okay, this is my condition. Okay, now what happens if A is greater than B, then the output will be true. If this is true, then the first expression is printed. If this is false, then the second expression is printed. Clear? So this is how the conditional operators will be working. And also you can do nested conditional operators also. Okay, that means within one conditional operator you can write other conditional operator also. That is called nested conditional operator. Okay, you can do that also. You can check that in the full length video. Okay, here I'm mentioning everything not in detail, but in order to, since everyone are familiar with, if you are familiar with Verilog, you will be familiar with all these operators. So I don't want to waste time on detailing explaining about these operators. So that is why I'm just telling like what are the, how the operator symbols will be there and what are the basic operation of these operators. Okay, and now coming to concatenation. So from the name itself you could say if you want to combine some 2 or 3 variables in one place, then you will be using this conditional operator. For example, A, B, C. Now if you are using this A, B, C, now all the variables within all the values within this A, B, C will be combined and you will be grouped together. Okay, so if you want to group 2 or 3 elements at a place, you will be using this concatenation operation. And then coming to replication, if you see here concatenation is having 2 braces and replication is 4, right? So replication means it is just replicate. What is the meaning? That means if you want to print the same for 2 or 3 times continuously, same value for 2 or 3 times, then you will be using this particular replication operator. Clear? Yes. And then delays and continuous assignment, you can also use as a we told you before itself, while you are writing a code in Dataflow modeling, you can also use delays. Okay, and again in delays you can have 2 types of delays mostly, because net declaration is not considered as most important thing. Mostly regular and implicit both are same. Okay, both, there won't be any change in the delays, but in the notation itself, like in regular assignment delay you will be giving the delay before the particular output variable. That means before LHS you will be giving the delay, but in case of implicit continuous delay, okay, here itself you will be giving the delay. Like at the, instead of writing SN you will be writing this particular result equal to IN1 to 5. Okay, so this is the notation. Like you have to remember this notation. If this is regular delay, you have to give it by using SN keyword. If it is implicit, that means implicit means within inside you are giving the delay. Okay, for that you don't need to use the SN keyword. You can just directly give the hash wave symbol. Okay, so this is about uh, mm, one part of Verilog. So I thought of making it into 2 parts so that it will be interesting for you also, and it won't be boring to watch the entire 2 or 3 hours of Verilog at one go. So that is why I'm just making this Verilog in one shot video into 2 parts. Okay, the second part will be in the next class. If you like this video, please consider subscribing my channel and hit on the notification bell also. Also, please do like it, and if you undercome any come under any VLSI aspirants, you can share this video for them so that it will be helpful for you. Hope this is helpful for you. Thank you.